Hello, Mr. Marvin. I was assigned a paper my name is Okello Andrew Peters. I was assigned a paper entitled A Quantum Optimized Approach for Breast Cancer Detection Using SqueezeNet Support Vector Machine or SVM. So this study basically integrates quantum-inspired optimization with deep learning, addressing critical challenges in medical imaging diagnostics. So let me start. Let me talk about the computational problem and problem formulation of this paper. So it is stated in the paper that breast cancer is one of the most aggressive forms of cancer and that early diagnosis can significantly improve survival rates. However, current computer-aided detection systems face three major challenges, which I believe are the computational issues here. Overfitting. Traditional models often fail to generalize across diverse datasets. Another one is high-dimensional data. Medical images like mammograms involve complex features that are difficult to process efficiently. Another one is annotation dependency, where most models require large annotated datasets which are time-intensive to produce. So the paper introduces a hybrid framework to address these issues. The proposed solution, which is SqueezeNet-SVM, combines a SqueezeNet for lightweight feature extraction, a support vector machine or machines SVM for robust classification, and quantum-inspired binary gray wolf optimizer, which is for efficient hyperparameter tuning. So the computational problem is framed as a classification task, determining whether a breast lesion is malignant or benign based on mammography images. So the approach innovatively integrates quantum mechanics principles, nature-inspired algorithms, and deep learning to enhance accuracy and efficiency. So how is this paper's methodology exploring multi-layer perceptrons? So although this paper, according to my review, does not explicitly implement a classic MLP, which is the multi-layer perceptron MLP, the principles of multi-layer perceptrons are evident in its use of SqueezeNet. However, it is important to clarify that the neurons in SqueezeNet do not behave like traditional MLP neurons. Instead of fully connected layers computing weighted sums and applying activation functions in a dense fashion, SqueezeNet relies on convolutional filters that extract spatial features hierarchically. So the neuron decisions in an MLP, neurons directly compute activations based on weighted inputs. In contrast, in SqueezeNet, convolutional filters act as feature detectors, emphasizing spatial relationships rather than purely numeric transformations. So the design decisions for activation functions here in this architecture, they used ReLU, which is also in full, it is rectified linear unit, is used in SqueezeNet to introduce non-linearity, because if they hadn't introduced ReLU, this network would only learn learn linear transformations only, or representations. But the moment they bring in ReLU, that means the network is able to capture non-linearity. So much like in MLPs, ensuring the network can learn complex patterns like subtle textures in mammograms. Another thing is biases. Unlike an MLP where each neuron has a dedicated bias, SqueezeNet's biases are distributed across convolutional layers and affect feature maps globally. While there are similarities, it is crucial to recognize that convolutional nature of SqueezeNet fundamentally differentiates its neurons from traditional multi-layer perceptron neurons, making it more specialized for image processing. So what is their neural network architecture? So this is my analysis concerning their neural network architecture. They have an input layer, they have hidden layers, and output layer. So in the input layer, the input to the network is preprocessed. Okay, the input, these are preprocessed mammography images converted to grayscale and enhanced for clarity using techniques like noise reduction and contrast adjustment. The hidden layers consist of fire modules, each performing compression and expansion to efficiently extract features. The bypass links ensure that critical details such as the texture of liaisons are retained across layers. So the output layer is the final layer, and it employs an SVM for binary classification, distinguishing malignant from benign liaisons. So SVMs are particularly effective for this task due to their ability to find optimal hyperplanes in high dimensional spaces. So this is the data flow summary in this architecture. Mammography images enter the input layer and undergo pre-processing. Features are extracted via the fire modules in the hidden layers, progressively refined through convolutional filters. The refined feature maps are sent to the SVM, the support vector machine, which classifies the liaison as malignant or benign based on hyperplane separation. So this structured flow of data ensures both efficiency and accuracy in classification, leveraging the power of deep learning while maintaining computational feasibility. So the activation functions and their impact. So the paper primarily leverages the ReLU activation function, which offers several advantages. The first advantage is efficiency. ReLU activates only positive values, making computations faster and less resource intensive. Another advantage is avoiding vanishing gradients. Unlike sigmoid, ReLU prevents gradients from becoming too small during back propagation, ensuring effective weight updates. Another thing to talk about is impact on pattern recognition. For instance, ReLU enhances the network's ability to identify subtle patterns in mammography images, such as irregular edges or faint calcifications indicative of malignancy. So what are the learning paradigms used in this study? So the study employs a supervised learning paradigm. Annotated datasets such as the CBI-SDDSM and InBreast guide the model to classify liaisons accurately. Why did they use supervised learning? This is because the binary classification task benefits. This is because of the binary classification task benefits from labeled data where the ground truth, which is malignant or benign, is known. Another thing is this approach ensures the model's predictions align with medical annotations, enhancing its reliability for clinical use. While reinforcement or semi-supervised learning could be explored in the future, supervised learning is ideal for the current dataset size and task complexity. So let me talk about the error correction and optimization. Error correction is a cornerstone of the proposed framework. So let's break it down. Back propagation. SqueezeNet uses back propagation to adjust convolutional weights, minimizing classification errors. Another one is gradient descent. So this optimization algorithm ensures the loss function is minimized during training, refining the model's predictions. So the QBGWO, which is the quantum inspired binary gray wolf optimizer, fine-tunes SVM hyperparameters such as penalty parameter C and the Kano coefficients by leveraging quantum rotation. They are called quantum rotation gets the QBGWO accelerates convergence and avoids local minima, enhancing model performance. So finally, let me talk about the applications of deep learning concepts here. Let's examine how deep learning concepts are applied. So feature extraction. SqueezeNet's fire modules identify critical features in mammography images such as liaison texture and boundary irregularities. And another thing we can look at is classification. So the SVM leverages these features to classify lesions with high accuracy. So the real world impact, for example, on the CBIS DDSM dataset, the model achieved when this model was run on with this dataset, which is CBIS DDSM, the model achieved accuracy of 99%, sensitivity of 98%, and specificity of 100%. So this performance underscores its potential for real-world clinical diagnostics, where accurate and early detection can save lives. So to sum up, the QBWO SqueezeNet-SVM framework represents a significant leap forward in breast cancer diagnostics, combining the best of deep learning and quantum-inspired optimization. Thank you very much. See you.